In the last video, we looked at useful stochastic processes, and in them we had a white noise. One of them was a white noise, and we said that a white noise is the building block for all the other processes. So today we are going to look at a moving average process of order 1. It is an MA1. We start by, we let ET be a white noise, or a purely random process with a mean 0 and variance sigma squared. Consider the model below. You have yt is equals to mu plus epsilon t plus theta plus epsilon t minus 1. That is a moving average process of order 1, where mu and theta could be any constant. The time series is called a first order moving average, denoted by MA1, as we have said here. The term moving average comes from the fact that yt is constructed from a weighted sum of the most two recent values of et. As you can see, the most recent values of et's. Now we can look at its mean. Its mean, we said we will just introduce expectation here, both sides. So expectation of yt is equal to expectation of our model now, mu plus et plus theta epsilon t minus 1. Expectation of a constant, that is a constant, so we have a mu there. Expectation of et is a 0. Remember we said that et is a white noise, which is usually normally distributed in the mean of 0 and variance sigma squared. Expectation of et minus 1 is the same as expectation of et, which is equals to 0. So meaning that expectation of yt is equals to mu, which is a constant. We can also look at the variance of the process. So we know that the variance of yt is given by variance of x from the simple definition of a variance. What is variance? Variance of x is equals to expectation of x minus mu squared. Using the same relation here, we have that variance of yt is equals to expectation of yt, the process, minus its mean, which is mu squared. Replacing yt with the process now here, we have that mu plus et plus theta plus epsilon t minus 1 minus mu squared. These two will cancel. So what we are left with is epsilon t plus theta plus epsilon t minus 1 squared. Squaring this term, we have that the first term squared 2 times this times this plus the last term squared. Now we distribute now our expectation. You have expectation of epsilon t squared, that will be the variance. Here we have expectation of theta epsilon t minus 1, this will be 0, since we said that expectation of epsilon t is equals to 0. So this term vanishes. The same case for so we have the last term here, we have theta squared epsilon, expectation of epsilon t minus 1 squared. Again, this one will be the same as sigma squared. So we will have theta squared sigma squared. So our final answer will be sigma squared plus theta squared sigma squared. You can see that sigma squared is common, so we can factor it out. So then we can have that we have now sigma squared into 1 plus theta squared. The result we have obtained here is actually the autocovariance, at lag 0. You can also look at the autocovariance at lag 1. Let us now look at the autocovariance at lag 1. The autocovariance is given by expectation of x, y minus expectation of x, expectation of y. Using the same relation, we have that expectation of x minus y multiplied by y minus its mean. Now, when we say that at lag 1, you can move one step ahead or backward. Let us move one step backward. Remember our model was yt is equals to mu plus et plus theta epsilon t minus 1. Now, moving one step backward, you have that yt minus 1 is equals to mu plus epsilon t minus 1 plus theta epsilon t minus 2. Now, the autocovariance function will be given by expectation of, using this expression here above, we have that yt minus its mean, yt minus 1 minus its mean. So when we subtract the both models, we subtract the mean, we will have this, and these terms will cancel, and also this term will cancel. So simply we will be multiplying the expectation. We have expectation epsilon t plus theta epsilon t minus 1 epsilon t minus 1 plus theta epsilon t minus 2. When you open these two, we will have something like this. And when you distribute now the expectation here, you will realize that the autocovariance function at drag 1 will be theta sigma squared. From the above computations, we can conclude that the process is stationary, and to be specific, it is weakly stationary. That is, we have seen that its mean is a constant, variance is also a constant, and its autocovariance at drag 1, we have seen that it is also a constant. We can also prove that the higher autocovariance is always equal to 0. How do we prove that? We let, now instead of, we use our the yt we are using, we have that yt minus mu, now yt minus j, we have not specified here, but in our lag 1 we used lag 1, but now we will not specify, we just say t minus j minus mu. But remember, we see that our yt was that model. Our yt minus j will be now mu plus epsilon t minus j plus theta epsilon t minus j minus 1. I've just tried to form this model in a similar way like this one here. So bringing in the expectation now for our autocovariance, we have that expectation of yt minus mu multiplied by yt minus j minus mu. We said that the mu's will cancel out, so what will be remaining for multiplication is epsilon t plus theta epsilon t minus 1 into epsilon t minus j plus theta epsilon t minus j minus 1. So opening the two and now introducing the expectation, bearing in mind that expectation of et is 0 and also expectation of et minus j is also equal to 0, we realize that this whole will be a 0. Hence, we conclude that we have proved that all the higher autocovariants are always equal to 0.